Yes, so hello students, welcome to IMS GATE Academy. Yeah, is it audible? Can you guys confirm the audio and video? Yeah. Can you guys confirm me the audio and video quality? So yeah, so those who are here, just can you please confirm me about the audio and video quality so that we can start, go ahead with the session. Yes, guys. Just a second. Yes, guys, can you let me know the quality, the audio video quality? Yeah. So Abhilash, good evening, Abhilash. Good evening, Souvik. Yes. So Abhilash, is everything fine? Audio video quality is good? Should we go ahead? Yes, good evening, Kundan. Yes, I'm good, Kundan. You came in the beginning of the yesterday's session and then you left. What happened? Is everything fine? Thank you, Vipin sir. Thank you. Just a second. Yes, Kundan. Yeah. Okay. Okay. So Kundan, is the audio video quality fine? Everything is fine? Yeah. Yes. Okay. So let's start with the compiler design. And as we Okay, thanks Isai. Thank you for confirming. Okay, so let us talk about compiler design, and as we discussed yesterday also, the aim of this session is to take you through all the topics that we have in compiler design in some roughly 3.5 hours. So right, so by 8:30, 8:15 we'll try to discuss each and every concept that is there in compiler design, and that way we will revise the entire content that we do in the class in around 40 hours. So the pace will be little bit higher because we do not have 40 hours to complete the subject. The main aim is again revision of the subject, right? And those, if there is very specific doubts, we can take those doubts also. That's not an issue, right? And what we will do is we will learn each concept through examples, right? So it will not be, again, as I discussed in the GATE score booster sessions, we did questions. In this session what we are going to do is we are going to learn the concepts, right? So in GATE score booster, what we do is we took questions which are highly probabilistic questions to come in the GATE exam, and here the revision is the major focus, right? I will take a concept, explain that concept, apply an example, and then that's it. So that is how we are going to cover the entire syllabus, right? So that is how the agenda of this today's session is. And so roughly, as we do in most of all my sessions, in almost all of my sessions, we'll first understand what is compiler design. So what do you guys think? What is compiler design? So designing of compiler is compiler design. So that can be one of the things to say. But yes, a better technical definition from from the engineers who studied at IMS also, and they also studied at in their colleges too. So what do you guys think? What is compiler design? What is it that we study in compiler design? And yeah. So what is it we study in compiler design? Yeah, tell me. So at least some answers are needed, because otherwise it becomes boring. Architecture of different stages, designing a good translator for user to interact with machines. Okay. So translator has different meanings, Kundan. So the definition which you have given, I would not say it is an incorrect definition, but saying such things will require a lot much explanation, because these are the terms which you are using. They are quite what do we say? Quite ambiguous terms, because translator has different meanings, right? Different phases of and how they work. Yeah, so that is the nearest to the definition. As Abhilash said, that we have to define, we are discussing what are the various phases of the compiler, how does a compiler works, what is behind each and every phase of compiler, right? What is the input of that phase, what is the output of that phase, and what exactly goes into that. So when we say only about input and output, that becomes a black box. But here, when we are discussing compiler design, we are actually trying to go deeper inside every level. So that is, we are doing something like a white box, that we are going to analyze each and every phase from inside, and we'll also analyze what is the input and output of each phase, right? So yes, and checking the correctness of high level language, even that is correct, Kundan. That definition looks better, right? So understanding the various phases of compiler, understanding, analyzing, and implementing the various phases of compiler. Understanding, analyzing, and implementing the various phases of compiler is basically compiler design, right? So that is how we can briefly define what do we study in this subject, and what does it all means when we say compiler design, right? So can somebody tell me how is it an application of theory of computation? So I generally say in my class in theory of computation that theory of computation has a direct application in compiler design. How do you guys think it is an application? How do you guys feel that theory of computation has its applications in compiler design? How do you guys think theory of computation has its application in compiler design? How do you guys think that? How do you guys feel this? 99% programming language is DCFL. Okay. So when we say programming, okay, so that is what you are trying to tell me is about the grammar of the programming language, right? Right, Kundan? What you are talking is about the grammar of the programming language. What I'm trying to understand is basically how it is an application of, so what is it? So for example, when we in TOC we see strings, we see automata, and what we do is we see that whether the string belongs to the language or not. That is what we do, right? In compiler design, in theory of computation. But when we come to compiler design, how do we say that it is an application of theory of computation? How does an automata comes into the picture? How does what does string looks like here? What does grammar looks like here? What does language looks like here? That's what I'm trying to understand. Are you getting my question? That how these two are interlinked, how TOC is an application of compiler design, that's what I'm trying to understand. So I know TOC, we discussed yesterday in TOC, in theory of computation, we make automata, and the automata takes a language, represents a language, and it accepts a language too. So for example, you give a string to the automata, and then it tells you whether this string belongs to the language or not. So how do we see that this is an analogy over here also? Okay. Abhilash says syntax analysis uses context-free languages to generate parse trees. Okay, good. What else? So what is a string here? What is a grammar here, and what is the language here, Abhilash? That is what I am trying to understand. Are you getting my question? So what is the string here, what is the grammar here, and what is the language here? Yes. So if a grammar is unambiguous and decidable, then we can design compiler. Okay. So Kundan, what do you mean by being a language being decidable? The properties of a language are decidable or not. You never say that a language is decidable. You know, the sentence which you have written is ambiguous, right? Is it okay? Is it okay? Kundan, are you getting my point? Yeah. Yes, we can automate if it is decidable. What do you mean by the language being decidable? This itself does not has any meaning, right? So let me define it for you guys. Let me define it for you guys. What I'm trying to say is basically in grammar. So when we study theory of computation, what do we see? That we have for example, we have a string in with us, right? So let us see over here. So when we see compiler design, when we see TOC, we have a string. We have a string, and this basically generates, and we have an automata to represent a language. To represent a language, we have an automata, right? And if the string belongs to the language, we say yes, and if the string does not belongs to the language, we say no, right? So what is the analogy here? That is what I'm asking here. So when we go to CD, what does my string becomes and what does my language becomes? What is my grammar now? So let us say now I have moved to compiler design. Now what is the string here and what is being belonging to the language means, and what does belonging to the not belonging to the language means? Are you guys understanding my point? What is it I'm trying to ask? Yes. Okay, okay. So somehow I believe that what I'm understanding from your answers is you guys know about compilers but do not know about the interlinking between the compilers and just a second. You guys do not know about the interlinking between the compilers and the, what do we say, the theory of computation. That's what my feeling is. So that's what I'm understanding through through the interaction that we have till now, that you guys are not very clear about this interlinking. So you have somewhere you have some parse tree in your mind, somewhere you have syntax analysis in mind, but there is no linking between the two subjects, which is very important to understand. So when I say compiler design, the string here becomes your C program. C program is nothing but a string, right? It's a character, it's a string, right? So all the lexemes that you have, all the tokens that you have, so basically that entire program is a string. And over here the grammar, so this is basically a string. String is basically your C program, right? And the language basically now over here is your C language. And then you use automata over here. So what is this automata that you use? The automata that you use is basically push down automata that you use over here. And then if the string belongs to the language, then you say that the syntax is correct. And if the string does not belongs to the language, you say that the syntax is incorrect. How do we do that? Based upon the grammar. So using the grammar rules, we try to generate the language, and we see that the string that you have is basically belonging to the language or not, right? So for example, one of the strings that I have is integer a, b, c. In this case, if I do not put a delimiter over here, if I just write integer a, b and c, and I forget to put the delimiter over here, it's basically a syntax error. So the string that you have generated is not following the rules of the grammar, and therefore you are unable to generate the parse tree for that, right? But what is working behind that parse tree? It is the pushdown automata is working behind that, because most of the languages are context-free grammars, right? Right? So are you getting this point or not? Tell me. So some part is CSL is like parameter matching, etc. Right, right. Okay. So what I'm trying to make you guys understand is the similarity between TOC and compilers is basically comes in the syntax analysis part, wherein your automata is pushed on automata, where your grammar is your C grammar, the grammar rules of the C programming language. Your language is C programming and C programming language, and your string is your C program which you have written, and I have to tell you that whether your program is syntactically correct or not. So that what does I mean by when I say syntactically correct or not? That is the program that you have designed is following the rules of the grammar or not. Right? Is it okay? Is everyone fine and so on the same page? Kundan, Abhilash, and who else was there? Kundan was there, Abhilash was there, and one more person was there. Just let me cross check. Yes, Kundan, Abhilash. Yes, Sovik, are you getting this point or not? Yes. Good. So now let us just quickly what do we do is we will add, we'll try to understand the various phases of compiler. That is the first thing that we have as far as the compiler design is concerned. So various phases of compiler. So guys, now I think you guys are going to tell me, and I'll just quickly keep on writing. If you have any issues, I will, I will explain that point in a better way, right? So just let me know what is the first phase for the compiler design. So what you get is a pure high-level language from the preprocessor. Pure high-level language that you are going to get from the preprocessor. What is it that comes first? The lexical analyzer comes first. Very good. So lexical analyzer comes first, and let me take an example string also side by side to make you guys understand what is happening in each step. So when we go to the next slide, let me take one more slide. So for example, the string given to you is x is equals to a plus b cross c. Yes, right. So x is equals to a plus b cross c. So can you guys tell me what will be the output of the lexical analysis phase over here? What will be the output of the lexical analysis phase over here? Yeah. So, okay, so I'm not asking you to count the number of tokens. What will the lexical analyzer phase do? That's what I'm asking. What will the lexical analyzer phase do? Yes, Abhilash, you are correct. So the lexical analyzer will read it as id is equals to id plus id cross id. So it will identify all the tokens in the program, right? Is everyone fine till this point? It will identify the tokens in the program, right? From the lexemes, it converts the lexemes. Lexemes is string of tokens. So from that, it will identify the tokens, right? Okay. So then, first of all, we have lexical analyzer. Then after that, we have, so lexical analyzer will generate tokens for us, right? So lexical analyzer is going to generate tokens for us. I will write the output here. It will generate tokens for us. Just let me undo. It will generate tokens for us. And then we go to the syntax analysis phase. So what is the input to the syntax analysis phase is basically tokens, and it will also take the grammar of the language from you so as to generate the string. So what will be the output of the syntax analysis phase? What will be the output of the syntax analysis phase? So yeah. So what is the output of the syntax analysis phase, guys? It generates a parse tree. Very good. So it will generate the parse tree for you. So it will generate the parse tree for you. Right? So syntax analysis phase will generate the parse tree for you. So what will be the parse tree in this case? So what is it missing? Can you generate the parse tree directly from here? What do you need now? To generate the parse tree, what do you need? Can I generate the parse tree directly from this language, from this string? You need the grammar. Very good. So let me give you the grammar. Let's say my grammar is E goes to E plus T cross T, and T goes to T cross F, and F goes to ID. Let us say this is my grammar. Let us say this is my grammar. And now what I'm asking you guys is, and so let me write one more production because that way you will need it. So let me undo it a bit. It is S goes to ID equals to E. Yes, so can you guys generate the parse tree for me? Can you guys generate the parse tree for me and tell me the number of reductions that you need to do to generate this? So if you do the bottom up parsing, the number of reductions that you need to do to generate this, can you guys tell me that number? Can you guys tell me that number? So Saptak says 7 reductions are needed. Okay, Kundan says 6. So who is correct? Saptak, Kundan, Abhilash. So how many reductions are needed? So say if I am trying to generate this using the bottom up parsing, how many reductions are needed basically? And you can also generate the parse tree for me. It's 5, Saptak says 6, Kundan again changes to 6. What do you think, Abhilash? What will be the answer? How many reductions are needed? So for example, if I will start from S goes to ID is equals to E. Now I can expand E, right? I can expand E. E will give me, E goes to E plus T, and T will give me T cross F. And F will give me ID. Over here, now this T will go to F, and F will go to ID. And over here, E will go to T, E will go to T, and T will go to F, and F will go to ID. So how many reductions are needed basically? So how do you calculate the number of reductions that you need? I would say 1, 2, 3. Your answers are incorrect. Those who have replied, your answers are not correct, guys. So just cross check. Did you guys got the same tree or not? Just first of all tell me this. Kundan Saptak, did you got the same tree or not? Abhilash says 7 now. So 1, 2, 3, 4, 5, 6, 7, 8. I can see 8 reductions. Please check. I can see 8 reductions. 1, 2, 3, 4, 5, 6, 7. So this is 1, 2, 3, 4, 5, 6, 7, 8. 8 reductions I can see, guys. Anand says 9 reductions. 9 is there. Just let me cross check. 1, undo. Okay, this is 1, 2, 3, 4, 5, 6, 7, 8. Right, I didn't count it this 9. So I can write it like this. Yes. So total are 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 reductions are there, guys. Right? Are you getting the point? Okay. So how do you count the number of reductions? Is basically you see the number of known leaf nodes. Anant, you don't have to count the internal nodes, you have to count the known leaf nodes, because that way if you only consider internal nodes, you will forget the root. Right, Anant? Are you getting my point? Right? So you have to take the root as well as all the known leaf nodes. So let us say it this way, just calculate the known leaf nodes. And this is just a trick which you can remember. So for example, they ask you that I was doing LR0 parsing, I was doing SLR1 parsing, I was doing CLR1 parsing, I was doing LLR1 parsing, and find the number of reductions. The number of reductions are not going to change. That's what the number of reductions will remain same. You just have to make the parse tree and tell me the number of internal nodes. Right? Is everyone clear with this point? Whether you do operator precedence parsing, LR0 parsing, SLR1 parsing, LLR1 parsing, CLR1 parsing, does not matter. The number of reductions are going to remain same. Is it okay? Right? And why I took only these names? Because these are bottom-up parsers. They are going to do the reduction. Right? And Anand, are you getting this point? These are known leaf nodes, not internal nodes. So number of reductions is basically is equals to the number of known leaf nodes. And over here I can see 1, 2, 3, 4, 5, 6, 7, 8 and 9 known leaf nodes over here. So that is why the answer will be 9. All good? Okay, good. So this is what we did. This is what we did in the syntax analysis phase. We created the parse tree. What does the next phase is? What is the next phase? Semantic analysis. So what does semantic analysis phase create? What does semantic analysis phase create? What does semantic analysis phase create, guys? Yes. Annotated parse tree, or we can also call it Anand, Kundan, very good. We can also call it semantically verified parse tree. That is also a well-known notation. Semantically verified parse tree. So what do I mean by semantically verified parse tree? That is everything. The type checking information, everything is done in this semantic analysis phase. Whatever is related to the meaning of the language, that is what we are going to do in the semantic analysis phase. So for example, type checking of the left hand variables and the right hand variables, the type should be same. But in C language, it doesn't matter a lot, because C basically what do we do is it does not, for example, the right hand side is a float and the left hand side is an integer, it will just chuck off the value of the float. Right? So C does the automatic typecasting. in such cases, right? So for example, and what might happen is basically if it is an integer and we are assigning it to a float, it will add 0 zeros at the end. So at least the type checking is bit loose here, but at the end of the day, if the languages are very strongly typed languages, in this case, you will require the type checking, right? So then we have this after semantic analysis, what is going to come? What is going to come after that? So we have done lexical analysis, syntax analysis, semantic analysis, and we got the semantically verified parse tree. And what is it after that? We have the intermediate code generation. Very good. Intermediate code generation. What does intermediate code generation do? It creates intermediate code, right? Very simple. The name itself suggests it generates the intermediate code. Right. So let me shorten it a bit so that I can finish it on the same page. So I have the intermediate code with me. So let us apply these two phases on the previous examples also. On the example that we took. So we have some 9 reductions and we have the parse tree also. That means it is okay. The semantically verified parse tree will only check the type checking. Will do the type checking and other information which is related to the meaning. So what else is an example of a semantic analysis? That all these variables should be declared. X should be declared, A should be declared, B should be declared, C should be declared. So all this is semantic information. Their storage classes, right? Their storage classes and their initialization, all this is checked by the semantic analysis phase of the compiler, right? Now after that, for example, in this case, if I have to generate the intermediate code for x is equals to a plus b cross c. If I want to generate the x is equals to a plus b cross c, if I want to generate the intermediate code, what is the intermediate code for this, guys? What is the intermediate code here? So one of the examples of intermediate code is 3 address code, and which is very heavily used, and this is basically the last phase of the front end of the compiler, wherein the code is portable to any of the machines, right? You can port it to any machine. Now tell me what will be the 3 address code of the given code. So what will be the 3 address code for the given code? Yes, tell me. Sorry. So Abhilash, if you should do multiplication first, not? Are you getting my point, Abhilash? You should not do addition first, you should do multiplication first. So T1 will give you B cross C first. Now T2 will be equals to A plus T1, and then you are going to assign X to T1, T1 to X. So this will be your 3 address code, right? Abhilash, do you get the mistake? Okay, good. So, and you can also check that, verify that information from the grammar also, Abhilash, right? So the grammar says that E goes to E plus T cross slash t goes to t cross f, and f goes to id. So that shows that multiplication has higher precedence because it is farther from the start symbol, right? So therefore multiplication needs to be done first. Okay, forget about C, you have to follow the grammar, not C, right? If nothing is given, then we will assume C. Is it okay, everyone? Everybody okay with this point? Right? Good. So now we have discussed all these phases. Now next phase that we have is, okay, I will write a bit bigger one, then I'll resize it again. So what will come next? After the intermediate code, we will have the code optimization. Code optimization. And code optimization is basically going to produce optimized code. And once you do the optimization, you go to the last phase known as code generation. Code generation. Code generation. Code generation, which will actually generate the code for you. What is this code? What is this code, guys? Yes, yes, Kundan, you are correct. Very good. You even told the techniques. We will discuss them, all of them today. Don't worry. So what is it that we are going to get? Assembly language. Very good, very good. So over here we are going to get assembly language. And all of these phases of the compiler are connected to the symbol table. So which is used by all the phases of the compiler. There is not even a single phase of compiler which does not use symbol table, and all of them are also connected to the error handler phase of the compiler. So whenever an error comes, if there is a syntax error, the error handler will, error analyzer or error handler I should write. So it will say error, the corresponding error whenever it is. So if it is a semantic error, it will say semantic error. If it is a lexical error, it will say lexical error, and so on and so forth. It will give you the details of the various errors, right? So I hope this overall picture of the compiler is refreshed in your mind, and now I can move ahead with the next things. Is everybody okay till this point or not? Tell me. Kundan, Abhilash, Sovik, Saptak and Anant. Is everything fine till this point? So yeah. Good, good. So now, since I have this with me, now what I'm trying to say is, okay, so we left the phases of the compiler in between. the output of this, so 3 address code. So for the example that we have taken, I left the example in between. So we had the 3 address code now. Now you tell me, once you have the 3 address code, what is it that you are going to produce now? From the intermediate code, you are going to optimize the code. Now, if you want to optimize the code, what are the various optimizations that you can do over here? So one of the optimization that is clearly visible to me is that this instruction is useless. What I can do is, sorry, x is equals to t2 over here. And if I can say that, I can write it like this also. Even this will also have the same impact as the previous one. So this is one optimization that can be done over here. Is it okay? So right, Kundan, there are various optimizations. I am just talking about the one optimization which is very much visible over here. Right? Yes, Abhilash, I understand the various techniques. We'll discuss that in detail, but I'm just discussing this example. And as of now, if I see whatever information is given to me, I can just reduce one instruction. That is one optimization. Reducing the number of instructions also is one kind of optimization that we have. Right? Is it okay, everyone? Yeah. So now last is to generate the assembly code for this. Generating the assembly code for this, and you know how to write an assembly code very well, right? So for example, what I can do is I can say, so again it depends from the architecture of the compiler, architecture of the machine that you are using, right? And what are the instructions that it provides. For example, load is there, store is there, move is there, which one is being provided, right? So let us assume that I have the move instruction with me. I am moving say B to R0, right? And this compiler allows me to keep one operator, one operand in the registers, in the memory itself. So add R0 comma, sorry, multiply R0 comma C. So multiply R0 comma the memory location C. And then I can say add, and the results get stored in R0. So again, when I am writing this, I have to tell you what are the instructions that are given by your machine. Only then you can write the assembly code, right? I cannot write it directly. So what is my assumption over here? I am having a machine which is providing me these kinds of instructions, wherein move is moving the value of B to R0. And multiply allows to multiply two numbers, stores the result in R0, and one of the numbers can be in the memory also, right? So similarly, add R0 comma memory location A. And once all this is done, then you have to move the result of R0 to the memory location C. Memory location X, sorry. Then you have to move the result to the memory location X. Right? So this is how all the phases of the compiler works on this example. Is everyone clear till this point or no? Tell me. Good guys. So this is all about the various phases of compiler, and if we talk about the the weightage of each part in the GATE exam, so all these things, the phases of compiler, then we have this lexical analysis, semantic analysis, then we have the code optimization, code generation, I should say intermediate code generation, all this will be one unit, and one major unit that you have is the syntax analysis unit, which is the most important unit of the compilers. Because this is basically the heart of the compiler, and this is again basically the heart of the questions which are being asked in GATE, right? And this will have somewhere around 1 to 2 questions from here. This is minimum and this is maximum. And over here you will also have 1 to 2 questions on the whole. So overall you will have some 2 to 4 questions in the GATE exam on compilers. So this is basically the overall structure of the GATE exam as far as compilers is concerned. Is it okay, everyone? Yes? So what we will do today is, we have already done this thing in detail. Now what we are going to revise, these 3 phases, these 4 phases, quickly refresh each phase within 15 minutes. So by 7, we will try to cover all these phases. And then in the remaining 1.5 hours, I will cover the syntax analysis, right? So till 7 we'll complete all this, and then till 8:30 we will try to complete syntax analysis phase in detail. What I'll do is, I'll take each and every parser and we will try, what we will do is, we will try to run an example on each parser that will give you a clear picture, and that will, refresh every parser's concept in your mind, right? I have to take an example to explain that, right? So is it okay, everyone? Is the plan agenda clear? So we are already done with this. We have to follow all these phases within 15 minutes, and then we'll directly move to the syntax analysis phase, which is the most important part, right? So Kundan, Sovik, Saptak, Abhilash, Anant, everybody on the same page? Should we move ahead? Yes, guys, please tell me. Is everything fine till this point? Yes. Okay. Good. Yes. Sovik is also okay. I hope Abhilash is also okay. Yeah. So Anand, you didn't come yesterday. What happened? You are very confident with theory of computation? Or you thought you just finished it, so there is no point on revising again? I hope the second one is more prominent. So I think we finished it on when? 7th of January. So I think that must be the reason, right, Anand? Okay. So maybe Anand replies meanwhile, and I think I'll give you a question. Again, on lexical analysis, let us try to understand what does lexical analyzer do. Can you guys tell me what are the basic functionalities of lexical analyzer? What are the basic functionalities of lexical analyzer? Okay. So what are the basic functionalities of lexical analyzer? What does it do? That is one thing, converting lexemes into tokens. That is one thing. Very good. What is the second thing that you think? Converting lexemes into tokens. That's what. What else it does? What else it does? Removing void spaces. It's not white space. It's called white space, Saptak. So whatever is the space is extra spaces is basically called white spaces. So removes white spaces. And third point is, it removes comments. It removes comments. right? What else it does? Removes preprocessor. Huh? Preprocessor is an entity. How can somebody remove preprocessor? No, Kundan, it's not correct. Nobody can remove preprocessor. Tell me what else it does. One more thing is left. Tell me. "30 seconds you guys to think." Yes, invalid tokens. Yes, that is basically covered. So we can the converting lexemes into tokens. If it finds an invalid token, it will generate an error. That's not an issue. What else it does? It counts tokens. Yes, counting lines is also correct. Very good. Identify the operator. Okay, correct. Now everybody is shooting arrows in the air. Maybe someone will hit me and I'll say yes. Okay. So okay, stream of characters stores info of the lexemes in symbol table. That is what Abhilash I was looking for. Yes, whatever you have said is correct. Kundan, you says counting the tokens, counting the lines, that's fine. Identifying the operator, that's fine. Creating the symbol table, again correct. Stream of characters, okay, that's fine. That is called lexemes. Mohammed, it is called lexemes. All the stream of characters is called lexemes, right? But it's not the functionality. It converts those lexemes into token is what it is, right? Right? And now what Abhilash says is what I was looking for, that it enters the line information of every identifier in the symbol table. So what do I mean by line information? The line of reference, line of declaration, line of usage, right? All this, because this is the only phase of the compiler which is going to read everything from line by line. All other phases will have different ways of reading the program, but this is the only phase of the compiler which is going to read the things line by line. Is it okay? So that is why once the symbol table is generated, so the symbol table will be generated by the symbol table generator. We have a separate entity for managing the symbols, but these are going to help the symbol table. All other phases of the compiler are going to help the symbol table, and they are also going to take assistance from it as and when needed, right? Is it okay, guys? Yeah. Okay, good. So this is what lexical analysis do, and GATE might have questions on what does this phase do, and one of the most important question that is everyone's favorite is to count the number of tokens. I took the same question in GATE Score Booster sessions and I find it very useful. It covers everything as far as the tokens are concerned, so that's why I have taken the same question. Okay, so just go through this and try to tell me the right answer. So you have to tell me the number of tokens in the below code snippet. Right? Count the number of tokens in the below code snippet. And this will, once we do this, the lexical analysis phase is complete. So you have some 2 minutes to count this. So Abhilash was there in that session. I hope he remembers this question. I think Anant was also there. Yes, Kundan was also there. Okay, good. So Souvik and Mohammed repeated the same mistake that Abhilash and Kundan did on that day. Yes. Please count once again, we'll see. So I have repeated this question is because this question itself contains everything. So you don't need to do anything else after this. Yes, not an entire function call, just the function name. Not sorry, entire function, not the entire function call, just the function name is one token. Yes, Anant, you are 100% correct. Good, Kundan. Avilas, just cross check. I think one mistake is there. Yes, good, good, Abhilash. Yes, greater than equals to is 1 and this is also 1. Right, correct. So Kundan has got the right answer, Anant has the right answer and Abhilash too has the right answer. And I'll just give you 30 more seconds for the others to give me the final answer and then I'll count it for you. Right, Abhilash, no issues. Good. Okay, so Saptak says explain it. Okay, so let me explain it now. Okay, so the answer is 78. Let us see how do we get at, right? So the number of tokens, let us count the number of tokens. I'll keep on writing the count at the top of it. This is 1, 2, 3 and 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Similarly, 4 from here, 20, 4 from here, 24. Till this 24, 25, 26. This entire is one thing, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38. Till this 38, 39, 40, 41 and this is 42. Till this we have 42 tokens. Right? Saptak is correct till this point. This is 42. Now coming back over here. So one thing is to remember is that the entire string inside the printf is one token, because string is a one token. This is a string, so this is a string. So string is always counted as one token, which is the point which has been asked multiple times in GATE. Right? So this question covers this. Now 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54. Then we have 55, 56, 57. So now always remember this ternary operator is one operator. And this greater than equals to is also one operator. So 57, 58, 59, 60, 61, 62, 63, I will not count this, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77 and 78. So that is how it will be 78. So I hope everybody got 78. If there is any confusion, ask me. What are the three things that you have to keep in mind while solving tokens question? This is one token. This is one token. And the string is one token. So if you keep these three things in your mind, you will never make the question on lexical analysis wrong. Okay, everyone? Right. So consider this token separately. Yes, it should not be considered separately because it's one token, right? One operator. Okay, everyone, should I move ahead? Please let me know. Is everybody okay till this point or not? Yes. Okay, Saptak, Sovik are clear, and I think Abhilash, Anant and Kundan have already got the right answer. So let me move to the next phase of the compiler. Answer was 78. And then comes semantic analysis phase. So, so when we talk about semantic analysis, what is important is to understand how, what are the various, if we talk about the terminology of semantic analysis, let me briefly discuss that terminology and then we will discuss how the questions come on that. So semantic analysis, basically, as the term suggests, we are going to do the semantic verification of the parse tree, right? So basically, over here, if we see, we have two types of attributes. So what is done in the semantic analysis phase? So every production will have a semantic action associated with it. And this semantic action can be a synthesized action or it can also be a what? Inherited action. So the attributes that are used here can be synthesized or inherited. So what do you mean by synthesized attributes and inherited attributes? Please let me know if you remember. If not, then I'll explain. What do you mean by synthesized attributes and what do you mean by inherited attributes? What do you guys think? What do we mean by that? So synthesized parent depends upon the child and inherited child depends upon the parents and sibling. Very good, Kundan. So in synthesized what happens is the parent gets the value from the child. So the parent gets the value from the child. I think it's quite, just a second. Let me use a different tip. So the parent gets the value from the child. And in inherited, the child gets the value from the parent or siblings. So for example, if it is A goes to BC, so if it is A goes to BC is the production which I am giving to you. So then in this case, A dot val is equals to B dot val dot plus C dot val. This is basically an synthesized attribute, but if I say B dot val is equals to A dot val plus C dot val, this is basically inherited. You are inheriting from your parents or your siblings. In inherited, so again Anand says, so let me read. Synthesized takes value from the children only, inherited take from siblings or the parents. That's perfectly correct. Synthesized from children, inherit from parents and siblings. So Anand asks, in inherited, synthesized can be take value from self. Yes, self values. So basically, when we are taking your own attributes, that is allowed in both. That's not an issue, but it is rarely a case when you take your own value. So when you are calculating something, you are going to assign and change your value. It's rarely that you are going to change from your own value, right? But yes, it should be allowed. It is allowed in both of them, in inherited as well as synthesized. Right, Anand? Although there are very few cases, and I have never seen such cases where you are inheriting or synthesizing from yourself. But if the situation demands, you can do that. That's not an issue, right? Okay. So now, so let me talk about two other definitions that we have: L values and the P values concept. Sorry, I should say L value left inherited and the right in S attributed and the left. Just a second. Let me. I have. I don't want this. Yeah. So what are the various types of attributed variables, attributed grammars that we can have? We can either have L attributed, or I should write S attributed this side, S attributed or L attributed. Yes. So over here, synthesized are allowed. Over here, synthesized as well as left inherited are allowed. Right? Synthesized as well as left inherited are allowed. Right? And over here, the semantic actions can be placed at the end of the production. So for example, A goes to B, C goes to D. Semantic actions will be placed at the end of the production. Here the semantic actions can be placed anywhere, like over here, or maybe over here also. So semantic actions can be placed anywhere in this, right? And the last point is, yes, how do we evaluate? So this evaluation is bottom up over here and top down over here, or you can say left to right, top down, top to down on last occurrence. And over here, left to right, top down on first occurrence. That's it. Is it okay, everyone? I think this got refreshed and rebrushed too. If there is any doubt, please let me know. And over here, since semantic actions are placed at the end of the transactions, at the end of the productions, we also call them postfix notation. Postfix. With this, we also call this as postfix. So they are at the end. The semantic actions are at the end, right? Right? So this will be left to right, top down in last occurrence, and left down, top down on the first occurrence of the variable. Is everyone clear till this point? Please let me know. Yes, okay, good. Kundan is fine. What about Anand, Souvik, Saptak? What is the situation, guys? And in this analysis, basically the questions comes on calculating the action, right? So they may ask you, they may give you a grammar and the semantic action, and they might ask you that what is this expression, what is it is going to produce if there are some print operation, or what is the functionality of the given code. That is also may be asked. That also may be asked, right? Okay. So consider the following grammar where semantic actions are placed in this. You have to tell me the output of the string. What will be the output if the string to be passed is xx, yy, zz, xxz? What will be the semantic action? What will be the semantic action if this is passed? So you have some 1 minute to solve this, and then I'll solve it for you guys. Okay, Sovik is correct, Saptak is correct. Or no, your guys are incorrect. Incorrect, guys. What about Anant, Kundan and Abhilash? What is the output? Correct, Anant is correct. Kundan is also correct. Abhilash is also correct. Very good. Just Saptak and Sovik, just cross check once and then I'll discuss the solution. Okay, so in whatever way it comes, you have to print the Sovik. So the answer will be 1323. Let me check it for you guys. It's 1323. Let's see. So let us generate the parse tree first. The parse tree will look like. I think I should go to the next page. Yes. So parse tree will look like S goes to XX S, and then I want, what do I want to generate? XXY XXZ. XXY XXZ. This is what I want. So this I have already got. Then YS. Then I want XX S, and then this S will go to Z, right? And how you are going to evaluate? Since this is the postfix notation, this must be inherited. This must be synthesized. So when you are going to print on the last occurrence of the variable, that is S. So you start tracing it. Last occurrence has not yet come. So now first last occurrence of this S has come. And what is the semantic action? Printing 1. So when this S comes, the semantic action is basically printing 3. When this S comes, the semantic action is basically printing 2. And when this S comes, the semantic action is printing 3 again. So the answer will be 1323. Answer will be 1323. Is everyone fine till this point? Should I move ahead? Should I move ahead? Yes, good. So now let's move to the next part. What is next part is intermediate code generation. So this is the, I think in the first part when we discussed, let me go back. So we are done with these two phases also. Now we are in code optimization and intermediate code generation. We'll complete these two phases in the next half an hour, and then remaining 1.5 hours we are going to spend on syntax analysis, wherein we are going to cover all the major 6 parsers in 15 minutes for each parser, right? Okay. So let's see. So what are the various popular representations of the intermediate code? What are the popular representations of intermediate code? What are the representations that we have? Yes, Kundar, I'll do that. Yes. Syntax tree, DAG is there, 3 address code is there, postfix is there. Yes, static assignment is also there, Kundan, but that's not a popular form. We have 3 popular forms. Yes, even I think Anant is also correct. Let me cross check it, and let me write down over here. And so what triples and quadruples are basically 3 address code representations, right? So they come under 3 address code. How do we represent a 3 address code? But when we talk about intermediate code itself, it can be written in either textual form or graphical form. And when we talk about textual form, we have 3 address code as the first way, and the second way is basically the postfix notation. In graphical form, you have syntax trees, abstract syntax trees, as well as what else you have? DAGs, directed acyclic graphs, right? Right, and you can have, so what is the difference in 3 address code? You are going to have 3 addresses in a single situation. So for example, x is equals to a plus b, this is allowed. So, 2 operands, 1 destination and 1 operator. So these things are allowed in a 3 address code. At max 3 addresses, 2 operands and 1 destination. And when we talk about postfix, again we know that x is equals to ab plus. So ab plus will be the postfix notation. And what is abstract syntax tree? So we draw the abstract syntax tree. It is same as syntax tree. It is basically the assignment is not written, instead the operator is written in between. This is basically abstract syntax tree. And when we talk about directed acyclic graphs, so over here if something is common, in that case we are going to have it. So for example, let me take one example for a So maybe if this is the case, so over here the common things are basically reused. So for example, A and B are adding them. And then what does C requires? It requires 2 iterations of this. So you don't have to redo everything, you can have such kind of a structure. But over here you will redo everything. So the common, it's kind of common sub-expression elimination from the abstract syntax tree. Is it okay everyone? Till this everything is fine? Yep, tell me. Yes, yes, good. So now you tell me what are the various kinds of instructions which are allowed in intermediate code. So one is, for example, I can have x is equals to y plus z for the binary operators. I can also have x is equals to op z for unary operators, right? What else I can have? Because 3 addresses at max I can take. What are the other kinds of instructions that I can have over here? Tell me. So I can have go to instructions. This is also allowed. I can have arrays. I can have pointers. Right? Yes, good, good, Kundan. You can copy. Assignment, this is called assignment. What else do we have? If. If x of y, then go to L. Right? Yes, this is conditional go to here. Right, Abhilash? So this is okay. This is basically binary. This is called unary. This is called assignment. This is jump, unconditional jump. This is arrays. This is pointers. And this is basically conditional jump. So this is basically the 3 address codes that we have. The 3 address code allows these kinds of instructions. Right? Is it okay? Right, everyone? So the 3 address codes allows all these kinds of instructions. Okay, good. So now you guys do one thing for me. Convert this code into 3 address code. Right. Good, good. So Souvik and Saptak, the 3 address codes are not allowed. 3 address code does not allow for loop. So you have to convert this entire code. Right? So maybe to save space, I'll move this up. Where is the pen? Hey Kundan, we'll cross check that. Others also please reply and let me know. Yes, please answer it, guys. Yes, so Kundan has also replied. Okay, so this comment I want to see. So, so you have marked the instructions from handed address, right, Abhilash? Okay. Okay. So I think everyone will have a different answer, and it is, tough to check in this limited time to check everyone's answer. What I'll do is, if you guys, everyone has attempted, let me solve it, and then you guys can check whether you are whether you are also doing the similar stuff or not, right? Okay. So let us do it. So over here, convert the following code into 3 address code that is being asked. And what is being given to us is for I equals to 1, I less than equals to 100, I plus plus. Okay. So the first is the initialization. This initialization is okay for me. I can write I is equals to 1 because it is direct assignment. So this is already a 3 address code. That's not an issue. Now I need to check, is it I is less than equals to 100 or not. So let me say if I is less than equals to 100, then go to some address. Maybe say go to loop. And what is the loop? Loop code is this. So the loop code is x is being assigned x plus 5 cross I. So first of all, I need to calculate 5 cross I, which is T1 is equals to 5 cross I. And then, so T1 is getting 5 cross I, and then I have to add x in this. So T2 is equals to x plus T1, and then finally x is equals to T2. So these are all 3 address instructions, right? Okay. What else needs to be done? Now you need to increment I. So I should become equals to I plus 1. So let's say T3 is equals to I plus 1, and now T4 is equals to I. I is equals to T3. And after that you will go to, let's say this is my instruction number. Let me call this address as start address. So then you go to start. Then you go to start. Right? And if this is not at this, then we'll do a unconditional jump to the end. And where is end? End is this. Right? So this is how the code will look like briefly. Right? So just let me know whether all of you are doing the similar things or not. Because Abhilash, I read your comment. It's very tough to read. It's like, so you have so this looks like exactly what is done by the lexical analyzer. All the white spaces are removed, so it's tough for me to read. So Kundan again, so it's in the same line, it's tough to read. Let me retry to do that. I is equals to 1, if I is greater than, go to L1. What is L1? L1 says this one. T1 is equals to, go to L2, L1 exit. Yes, so Kundan, if you can write it in different lines, it will be more readable for me. Without spaces, it's very tough to read and comprehend what you're trying to do. Right? So maybe you can write in different lines. But if the functionality is same, it should work out, Kundan. It should not be an issue, right? Okay, it comes in one line, so it's very tough to read it this way. So what you are doing is you are assigning 1 to I. That's fine. L2. What is L2 is a placeholder, Kundan. L2, if I is greater than 100, go to L1. So then it's fine. It should work. Not an issue. Let me cross check once. If L2, then you are saying L2 is if I is greater than 100, go to L1. L1 is your loop location. So where does L1 starts? You have not specified. Actually, if I is greater than 100, then you're going to exit. That's fine. Okay. Otherwise, you are doing T1 equals to 5 cross I, x equals to x plus 1. T1 and I is j, I equals to I plus 1. Right? Go to L2. Then you go to L2 again. Okay. And you do the checking and exit. This is also fine. You can also do it like this, Kundan. It's not an issue. Yeah. Right. Right. Okay. Okay. Right. So I think, is everyone okay till this point? Should we move ahead? Now let me know whether everyone is on the same page or not. Right. Good. Kundan is okay. What about Abhilash, Anant, Sovik, Saptak? Just let me know. What is your status? Okay, good. Abhilash, what is your status? Is everything fine? Should we move ahead? Yes. Okay, good everyone. So let's talk about code optimization. That is the last phase, and after that we'll come to the most important phase, that is syntax analyzer also. So till this, whatever we have covered, we'll have 1 to 2 questions from this part and remaining 1 to 2 questions from syntax analyzer part. So we'll try to finish it within 5-10 minutes, and then the rest will another 1.5 hours we'll only talk about parsers, right? So okay. So code optimizations, again, I think there are a lot many optimizations. We'll do a few of them. I'll just quickly recap a few of them and then we'll move ahead. So the first one that we have is basically, what are machine independent optimizations? Machine independent is that it is not dependent upon the type of the code, on the machine type. So it's basically a machine independent optimizations, and then we have machine dependent optimizations too. So there are two types of optimizations that we have. So sometimes we have machine dependent optimizations, sometimes we have machine independent optimizations. Sometimes the optimizations are on the local code. Then we call them peephole optimizations. And sometimes they are, you need to look the overall code, then they are not peephole optimizations. Right? So this is how we are basically trying to divide the kinds of optimizations that we have. Right. Okay. So okay. So then we have basically, let us talk about the various loop optimizations that we have. What is the first loop optimization that you guys see? Is basically loop jamming. It is also known as loop fusion. It is also known as loop merging. What is this, guys? Tell me. The name itself suggests that. So, right. So, the name itself suggests that. What is it? Yes, Kundan, you are 100% correct. You are merging two loops into one loop. For example, I have a loop says for I equals to 1, I is less than equals to 10, I plus plus, there is one loop, and there is another loop which is also there, which is also running for 10 times. So what I can do, if the functionalities are independent, I can merge these two loops into one loop. Right. Okay, so this is called merging the loops. What else we have? Loop. Loop merging is done, loop fusion is done, and then loop is loop unrolling. So what is loop unrolling? And it is also called as loop unwinding. So what is loop unrolling and unwinding, people? So for example, if it is for I is equals to 1, I is less than equals to 100, I plus plus, and I say printf gate 2023, so basically I can unroll it, make it 50, and write printf gate twice, and so on. I can simply unroll the entire loop and write it 100 times. Even that is also okay. Okay? Okay, right. Good. So Kundan, can you please use the smaller, the small case, because reading the capital case is a bit tougher, right? So yeah, yes. So then what else we have? Last one is loop unrolling is done, loop unwinding is done, and we have also done loop jamming and fusion, and that is also called loop merging. And what else we have? Loop, so we can merge, and then we have code motion. So what is code motion? This is also known as code motion and frequency reduction also. We can also call it code motion as well as frequency reduction. Or we can also call it loop invariant. Very good, Anant. Very good. So what we are trying to do is basically whatever is independent of the loop may be moved outside the loop. For example, if I am doing A is equals to sin x divided by cos x, all this is independent of the loop, you can move it outside the loop. Right? So you can move it outside the loop over here. Right? So thereby the number of instructions that are executed are reduced and the effect remains the same. Therefore, we are trying to optimize the loops. Right? So what are some other optimizations? Let us say one optimization that we have is algebraic simplification. Then we have redundant code elimination. Then we have is strength reduction. Then we have constant folding or constant propagation. What are these terms? So common sub-expression elimination is basically redundant code elimination, right? It is same as that, common sub-expression elimination. Right? But it is different from dead code elimination. The code which is never reached is basically dead code. Yes, that is basically Strength reduction, basically, Kundan, what you are suggesting. Right? So for example, when we talk about algebraic simplification, one of the things that can be done is, so for example, a is equals to a into 1. So this 1 can be removed. A is equals to a plus 0. So this 0 can also be removed. Right? Now when we talk about redundant code elimination or the common sub-expression elimination, is basically x is equals to a plus b, and then let's say y is also a plus b plus c. So what we can do is y can be replaced by x plus c. So this expression can be replaced with this one. Strength reduction. So using better operators. So for example, I am a is a multiplied by 2. It is as good as a is being shifted 1. So this is a better operation that we have. Right? Then we have the constant folding or constant propagation. Constant folding and constant propagation is basically 2 plus 3 plus 5 is being assigned to A. So why you are doing this? You can simply write it as 5 plus 3, 8 plus 2, 10. So constants are folded. Right? So you are folding the constants. That's also one of the optimizations. Right? That is also one of the optimizations that we have. Right? So that's all about, do we have others? Like I think, like for example, you must be knowing about jumps. Jumps on jumps should be avoided. Then you can also use machine idioms. Like for example, if a machine allows increment operation in itself, you should use that increment operation, right? Yeah. Okay. So these are like, this is basically dependent upon the machine which you are using. If it is there, then we can use. And then sometimes there is redundant load and store. So for example, what you are doing is you are storing a variable. So for example, you are storing a variable x and after that you are again reloading it. So for example, you are storing a variable and then again you are reloading it. So for example, a is equals to b plus c, and then this again z is equals to a plus d, say. So you should not store back this a again. You can simply keep it there, and because if you store this again and then you again load it, this is waste of the CPU cycles. Right? So CPU will be idle at that time. So therefore don't, so if there is, if it is a store as well as load, you can avoid that. Right? So you know, if a load is directly followed by a store, then you can do that. Right? Is it okay? Okay. So this is all about code optimizations, and I think if this much is brushing of the concepts, brushing up of the concepts, so as far as code optimization is concerned, it is more than enough. Yes, so people optimizations are all local optimizations, as I mentioned previously also. Yes, so all local optimizations wherein you don't have to look at the global things are basically peephole optimizations. Right, Abhilash? Okay. So that's where the word peephole comes from. So you are looking at some part of the code. You are not looking at the global code and then trying to do certain optimization. So whichever optimization is local is basically a peephole optimization. Right, Abhilash? Is it okay? Right? Should we move ahead? Guys, please tell me. Is everyone fine? And should we go towards the last and the most important phase, that is syntax analysis? So till this we have covered 50% of the the weightage of the gate as far as the gate is concerned, right? Okay, so Abhilash is okay, Kundan is okay, Saptak, Souvik and Anant. Yeah, Anant is also okay. What about Saptak and Souvik? Right, Saptak is also okay. Souvik, what's your status? Everyone fine? Okay, okay, Abhilash, no issues, no issues. Good. So now let's talk about syntax analysis. So this is the most important phase of the compiler, as we know, and this in this phase basically the compiler is going to take the string that you have written your C program, right? And basically what it is going to do, it is going to generate the parse tree. If you can generate the parse tree, you are certifying the fact that the program that you have written is syntactically correct. So what is behind that? What is behind that analysis is basically the push down automata, right? Right. So overall C is basically so the grammar of the C is basically a context sensitive grammar because it has the semantics also. So semantics require context sensitiveness, although, but otherwise the syntax analysis part is completely can be handled by the context free grammars, right? So the grammar can be handled by the push down automata also, right? And the lexical analysis can be handled through the finite automata through also, because there you are just doing the matching, right? So therefore in the syntax analysis phase we study various approaches. Let me just briefly highlight all the approaches so that so everything gets refreshed. So you have the different parsers with you. So some are called top down parsers and some are bottom up parsers. And when we talk about top down parsers and bottom up parsers, this is what we are discussing now. Now top down parsers we have, what are the various top down parsers that we have? Tell me guys, what are the various top down parsers that we have? Yes, tell me. What are the various top down parsers we have? Yes. So top down parsers with full backtracking. That is basically we have brute force approach. Now what is top down parsers with? Otherwise we have the recursive descent parser, and then we have over here we have non-recursive descent parser. Right? Okay, and these two both are without backtracking. These are without backtracking. And LL, this is also known as, this is the most important one as far as the bottom up is concerned. This is also known as LL1 and also known as predictive parser. Now, what is a bottom up parser? Give me the examples for bottom up parsers. Give me the examples for bottom up parsers. Yes, right, Anand, very good. So over here we have operator precedence parser. Let me move it a bit over here, otherwise it will jam with this. So we have operator, So we have, right? We have operator precedence parser and we have LR parsers, and there are various types of LR parsers we have. We have LR0, LALR1, LR0, LALR1, SLR1 and CLR1. All these are LR parsers, right? And all these bottom-up parsers are also known as SR parsers. All these bottom-up parsers are also known as SR parsers. Right, that is called shift reduce parsers, right? Because shifting is known as pushing and reduction is known as popping, right? Right, I think that's all. That's all about the classification of parsers. Classification of parsers. Yes, okay. Right, so when we talk about this brute force approach, when I talk about this brute force approach, what is it that we do? Is basically we are trying to generate from the top down, and whenever there is a mistake, we go and backtrack, right? So what is the complexity of this brute force approach in general? What is the complexity of the brute force approach? Yes, tell me. What is the complexity of the brute force approach? Exponential complexity. Very good. But what can you number that complexity? We derived it in theory of computation class. What is the number? If number of productions that you have is P, mod of P, and the number of what do we say? You also have the length of the string is mod of W. So can you define what will be the complexity? Yes, Anant, you must be knowing it. Abhilash, Anant, we discussed this in class. So this complexity comes after simplification, that is removing the unit productions, after removing the null productions, and after removing the useless productions. Then you must be knowing what will be the complexity. We discussed this in class. So if the number of productions that you have is mod P, and the number of productions that you have is mod of P, and the length of the string is mod of W. Just let me know the expression. Anand, do you remember? Are you checking or should I reply? So it comes out to be mod of p raised to power twice of mod of w minus 1, which is exponential, right? Because that many steps are needed, these many steps are needed for generating the string, and you have at every step you are having mod p number of productions, so you have to use one of them, right? So this is basically roughly the complexity that we get. And what is basically a recursive descent parser? What do we do in recursive descent parser? So in recursive descent parser, we are going to have functions for every non-terminal, right? We are going to write functions for every non-terminal. That is how we are going to generate the recursive descent parser, right? And it is going to use the operating system stack. It does not have any stack of its own. So these are the two things that you should keep in mind. And it's not a very important topic. It has rarely been asked in GATE, right? But anyways, we should know it. Nobody stops them from asking it this time, right? Okay. So this is basically in recursive descent, just one thing needs to be remembered, that you are going to write functions for every known terminal, right? And then basically you are going to check. So for example, if there is a production of the type A goes to plus BC, you are going to check this first, and then you are going to call B as well as C after that. If the production is of the form A goes to plus BC, right? Okay. So this is basically non-recursive descent parser. Sorry, recursive descent parser, and then let's come to LL1 parser. Let's come to LL1 parser. Right. So before that, before we go ahead with LL1 parser, we need to have the knowledge of first and follow. So you guys need to find out the first and follow of every terminal, every non-terminal in this grammar. So just let me know the first and follows. So let me know the first and follows here. So when we talk about any parser in detail, in general, what we have is basically we have a, just let me wait for a moment. Let me clear this point also. So whenever we have a parser with us, we have a parsing table. This is the parsing algorithm that we have. Then we are going to basically have a stack and basically an input buffer. So wherein your string will lie. So what happens basically, the parsing algorithm looks at the stack top, looks at the input buffer, it consults the parsing table, and then it takes the action. So this is how is basically the overall design of the most of the compilers that we are, not most of the syntax analyzers that we study, right? Is it fine till this point, everyone? Please tell me, this got refreshed or not? So if you guys are not remembering, then just ask me the doubts if there is any. But keep on responding, otherwise it becomes boring for me if nobody is responding. Yes, yes. Kundan is okay, Anant is okay. What about Abhilash, Saptak, Souvik? Right? Okay, good guys. So now, find out the first and follow for this grammar, and then I'll explain briefly how do we calculate first and follow. Audible? Is it audible, guys? Yeah. Yes, yes. So, I think almost many of you have answered it. So, tell me what do we mean by the first of a non-terminal? What do we mean by the first? What do we mean by the first of a non-terminal? Yes, good evening, Aman. So, what do you mean by the first of a non-terminal? So, when we are finding first of a non-terminal, what do we mean? Terminal which appears at the first symbol by strings produced by the non-terminal. Right, right. So, whichever terminals, right, Ganant, you are correct. So, whichever terminals are coming at the beginning of the strings which are being generated, which are the first symbols that are being generated in the strings, whatever strings can be generated from that non-terminal, all the terminals which are coming in the beginning are called the first of that non-terminal. And what do we mean by follow? What do we mean by follow? What is the meaning of finding the follow? So, this is first, and what is follow? Okay. So, the next terminals after first class, after first or first of the next non-terminal, that is the next after first or first of the next non-terminal. No. The symbol after that particular non-terminal, no. That can appear after non-terminal. That is correct, but again, not no one is 100% correct. Everyone is partially correct. So, all the terminals which can appear after that variable in the process of derivation, they are called the follow. Is it okay, Abhilash, Anand, Sovik? Are you getting my point? What all can come after that non-terminal in the process of derivation, what immediately follows it is basically the follow. All the terminals which immediately follow that variable in the process of derivation is called the follow, right? Okay. So, let us see. So, in general, I hope you know how do you calculate first and follow, but in general, let me briefly define that and then we will come back to this example, right? So, how do we calculate first is basically, for example, if you have to calculate a first, means first of A, if this is the production, so first of A is basically nothing but first of BC, right? Am I correct? First of A is first of BC, and this is where we go. And when epsilon comes into the first, epsilon comes in first if and only if that is the only non-terminal, if and only if that is the only non-terminal, if and only if it is produced by that, if it is produced by that non-terminal. Is everybody okay till this point? Regarding first, right? And when I say follow, how do we calculate follow? Tell me what will be the follow of A goes to B alpha, where alpha is a terminal. A goes to B, so tell me follow of B. A goes to B, C, tell me follow of B. Tell me follow of B. Similarly, A goes to B alpha. A goes to B, tell me follow of B. Tell me. So in this case, follow of B will be alpha. In this case, follow of B will be first of C. And in this case, follow of B will be follow of A. So it's not directly equal. You are going to apply the algorithm. You are going to apply the algorithm and take on union. So it should be, I should write it as follow of B is nothing but follow of B union alpha. Over here I should write follow of B is equals to follow of B union first of C. Over here I should write follow of B union follow of A. Right? This is how the algorithm will work. Right? Now tell me, can dollar, so dollar is always in the follow of the first symbol that we have. Dollar is always in the first symbol. Dollar is always there in the first symbol of the grammar, is always in the follow of the first symbol of the grammar, that we know already. Right? So these are the three, 4 points that you should keep in mind while calculating the follow. And another important point, epsilon never comes in the follow of any non-terminal. Why? Because at the end of it, you are always going to find dollar. So epsilon never comes in the follow of any non-terminal. Is it okay? Is it okay? Right? And the follow can also be an empty set if that terminal is unreachable. So these are the 5-6 points. If you keep in your mind, you will always make the follow and follow things correct. So for example, I'll just let me mention follow of start symbol always contains epsilon, sorry, dollar. Epsilon never comes in follow of any non-terminal. And the last thing is, follow can also be phi if that non-terminal is unreachable. Right? It can be phi, epsilon never comes, and start symbol will always have dollar. Right? Is it okay, everyone, on the same page or not? Tell me, guys. Okay, good. Now let us calculate the follow of our example. The first and follow for our example. What I am doing is I am writing first of the E on this in the row corresponding to E. Over here for E dash, over here for T, over here for T dash, and over here for F. So over here for F. So what is the first of F? ID comma open brace. What is first of E dash? Plus comma epsilon. T dash multiply comma epsilon. First of E is equals to first of T. What is first of T? I have not yet calculated. First of T is first of F. What is first of F? ID comma open brace. First of E is nothing but first of T. First of T is ID comma open brace. Is it okay? Now let us calculate follow. Let us calculate follow. Now how do you calculate follows? Whatever follows that variable. So first of all, when you have to find out the follow of E is the start symbol, therefore follow of E always contains dollar. Now wherever E is coming on the right hand side, where you find it, it is there. So follow of E will also have closed brace in the follow. Right? Till this point, fine. Next is follow of E dash. Now from this, if we see, follow of E dash is equals to follow of E. What is follow of E? Follow of E contains dollar comma closed brace. Now follow of E dash is equals to follow of E dash, that we know, there is nothing new. Right? Till this point we have found out follow of E dash. Now we have to find out the follow for T. Now follow of T is nothing but first of E dash. Now what is first of E dash? First of E dash is plus comma epsilon. I add plus over here. Now epsilon never comes in the follow, but because of this epsilon, this vanishes and follow of T becomes equals to follow of E. Therefore follow of E is basically dollar comma epsilon or dollar comma close brace. I added to it. I add to it. Right? Now after that, follow of what? T dash we have to find. Now follow of T dash is nothing but follow of T. Follow of T dash is nothing but follow of T. What is follow of T? I just calculated. It is plus comma dollar comma close brace. Over here it says T dash, follow of T dash is equals to follow of T dash. I know this already. Now follow of F. Follow of F is nothing but first of T dash. First of T dash. Now let us find first of T dash. First of T dash is star comma epsilon. Epsilon never comes in the first, but because of that virtue of that, by the virtue of that, follow of F will become equals to follow of T dash, and follow of T dash I have just calculated above. It is equals to this. So this is how you calculate first and follow for this example. Is everyone okay till this point or not? Tell me. So we have laid the foundations for LL1 parser. Now let us try to cover that parser in detail using an example. Right? Good. Very good. So let me take the same language and generate LL1 parser. So first of all, whenever I am discussing on parser, I will generate the parsing table for that parser. So let us construct the LL1 parsing table. Tell me what are the rows and what are the columns in the LL1 parsing table. Tell me guys. What are the rows and what are the columns in LL1 parsing table? So before we do that, you have to tell me what are the conditions for a grammar to be LL1. First of all, there should not be any non-determinism. Non-determinism is not allowed. Ambiguity is not allowed. Then what else is not allowed? Non-determinism is not allowed. Ambiguity is not allowed. Left recursion is not allowed. And conflict in the parsing table is also not allowed. All this is not allowed. If a language does not have any of these things, then it is called LL1 grammar. So left vectoring is a technique to remove the left recursion, Kundan, right? So these are basically the conditions for a grammar to be LN1, and this is a very, a very frequent question to check that whether the grammar is LL1 or not. You make all these checks and then you can tell me whether it is LL1 or not. So if you see this grammar There is no non-determinism or anywhere. Anywhere you will never find non-determinism. So this is T, this is plus, this is epsilon, this is F, this is multiply, this is epsilon, this is ID, this is open brace. There is no non-determinism anywhere. So there is no non-determinism in this grammar. Ambiguity. So ambiguity is not very easy to find, as I always say. Therefore, you just directly move to the conflict in the parsing table thing. If the ambiguity comes to your mind, then that's a different thing. But in 99% of the questions, you will find that conflict in the parsing table implies ambiguity, right? Although ambiguity is an undecidable problem, right? So therefore, if that implication would have been 100% correct, that is, conflict implies ambiguity, then definitely if the implication is both ways, then there is a problem, because that way that way our problem will become decidable. But it is an undecidable problem. In 99% of the cases that you find, the conflict in the parsing table will definitely provide you ambiguity. So therefore, you don't need to check much for it. If the ambiguity comes to your mind, then it is fine. If the ambiguity does not come to your mind, then go ahead, right? And how do you check ambiguity? In general, you make two parse trees for the same string. So you have two challenges. You have to find the string and then you have to generate two parse trees. Okay, is it okay till this point? Now left recursion. Left recursion. Do we see any left recursion over here? No, not even a single thing is matching. Is T, E dash T plus E dash epsilon, TF, T dash multiply, T dash this. No, not even a single left recursion is there. So what is left recursion? A goes to A alpha. This is left recursion. What is non-determinism? So for example, A goes to A or AB. Now this is non-determinism. Which one is to be chosen? You don't know, right? Now conflict in the parsing table is what we are going to check now, and we will construct the parsing table for this grammar, and that way we will revise the parsing table concepts for LL1 grammars. Now tell me, how do we construct LL1 parsing table? What are the rows and what are the columns? What are the rows and what are the columns? So tell me, what are the rows and what are the columns? I will require all this. Okay. If I remove this. I need to take a screenshot now. So tell me, what are the rows and what are the columns? First and follower columns? No. Okay, so the non-terminals comes at the columns. So let me write the non-terminals here. What are the non-terminals? E dash, T dash and F. So these becomes my non-terminals, and what are the terminals? They come on the columns. So we have plus, multiply, ID, open brace, close brace and $2. Lot of stuff is there. Okay. Undo. So we have plus, multiply, ID, open brace, close brace and $2. Right? These are basically the rows and columns. So how do you make entries? Basically, what you are going to do is, so you will calculate, so for every production you will number them. Maybe let us, this is 1, this is 2, this is 3, this is 4 and this is 5. Oh, there is another production, but let us call it 3, this is 4, this is 5 and this is 6 and this is 7. Okay, let me undo everything. This looks a bit confusing. This is 1, 2, 3, this is 4, this is 5, this is 6. This is 5, this is 6 and this is 7 and this is 8. So we have some 8 productions. So for every production, so okay, so 1, 2, 3, 4, 5, 6, 7, 8. 8 productions you have. Right. So 8 productions we are having, right? So right. So how do we fill the productions? How do we fill this table? What do? We calculate the first of the right hand side and we place that production in that. If the first of the right hand side contains epsilon, then we are going to calculate the follow also. We are going to place that production over there also. Right, everyone? Right? So how do we do that? So let's do it for the first one. E goes to TE dash. E goes to TE dash, and now tell me what is the first of TE dash. First of TE dash is first of T. First of T is ID comma open brace. First of T is ID comma open brace. I have already calculated. So I will place this first production over here. I'll place this first production over here. Oh. Is it okay? Is everyone fine till this point or not? Tell me. ID comma open brace I have put. Saptak, Sovik, Anant, Abhilash, are you there with me or not? Sovik and Abhilash, are you there or not? Yeah. Okay. So after that, next production is E dash goes to plus TE dash. What is the first of plus TE dash? It is just plus. So I'll place number 2 over here. Now what is first of E dash goes to epsilon? First of epsilon is epsilon. So then when the first contains epsilon, then you are going to place it in the follow instead of plus. So in the follow, what is follow of E dash? It is dollar comma closed brace. Okay, just a second. Yes, okay, it's correct. So dollar comma closed brace will have number 3. Right till this? Okay, good Abhilash. So now T goes to FT dash. T goes to FT dash. So when we have T goes to FT dash, what is first of F? First of F is basically ID comma, first of F is ID comma open brace. I'll put it in that. So T wala will come in ID comma open brace. ID comma open brace. This is number 4, number 4. This is number 4 and 4. Right? Right till this point? So how the questions will come? There are 3 kinds of questions. One is, tell me whether the grammar is LL1 or not. We have written the check. What is the check? You have to check whether there is non-determinism, whether there is, it should not have any non-determinism, it should not have any left recursion, it should not have any ambiguity, and there should not be any conflict in the parsing table. Second questions can be on the configuration. Tell me the contents of the parsing table. They may ask what is PT of E dash comma plus. E dash plus is 2, right? So that is the contents of the parsing table may also be asked for. And the last thing that they can ask is basically the configuration during the parsing. how does the stack looks like, where does the input pointer points, they can ask in that terms also. So what we will do is we'll do this for all the parsers in the next 1 hour, and that way we'll be able to have a good clarification on all the parsers that we have, right? Okay. Right? Okay. Tell me guys. So next is 4, 4 is done. Then T is done. For this is the 4th one. For the 5th one, ID, open brace is done. For 5th one, it is just multiply. 5 will come over here. Now this will come into the follow of T dash. Follow of T dash. Now what is follow of T dash? Plus, comma, dollar, comma, closed brace. Plus, comma, dollar, comma, closed brace. Is plus, comma, dollar, comma, closed brace. F goes to ID. First of ID is ID. 7 will come over here. And first of open brace is open brace. So 8 will come over here. Is the parsing table clear, everyone? Over here, all these other entries are error entries. So this is how you fill the parsing table. Right? This is how you fill the parsing table. So what is the idea? Go to every production, find the first of the right hand side. If the first of the right hand side, and place that production into the whatever is there in the first, that becomes the column and the row becomes the left hand side. If the first contains epsilon, then place the production in the follow of the left hand side. So the follow of the left hand side becomes the columns and the row remains the left hand side itself. Right? Right? Okay, good. So let me just resize it a bit so that I have space for parsing a string in this grammar. So this completes the parsing table for LL1 parser. Now tell me, so the size of this table will be number of terminals mod of V cross mod of T plus 1, Y plus 1 for dollar. Okay, Kundan, is it okay? Right? Now you tell me, let me give you a string in this grammar. The string is ID plus ID. Can you guys generate the parse tree for this? Parse tree for ID plus ID. Please generate the parse tree for ID plus ID. अरे क्यों नहीं बन रहा? बनेगा? You should get ID plus ID. What is the issue? Just cross check once. Are you getting ID plus ID or not? Yeah, is it audible now? Is it audible now? Yes, Anand, did you got the same tree? Yes, good, good. Yeah, can you guys confirm about the audibleness? Is it okay now? Yes, okay, good, good. Okay. So this is the tree that you will get, right? And how many? So when you are doing a top-down parser, you are going to expand. How many times you are going to expand? This is the first time you expanded. Then you expanded the second time. This is the third time you are expanding. This is the fourth time. And then, so expansion is same as reduction, right? So either you will expand or you will reduce. So how many expansions will be? The number of expansions will be number of reductions. So let us count the number of reductions. That is easier to count. Yes, is it audible, everyone? Can you cross check? Is it audible now? Yeah. Can you guys check? Is it audible? Are you there or not? And so Anant, Kundan, Abhilash, Shaptak, can you just cross check and let me know, is everything working fine? And also let me know whether you could parse this or not. So whether you could parse it or not, tell me. Okay, so audible now, I think, yeah. So there was slightly some battery issue was there. I hope it doesn't arise again. Okay. Right. Good, good. So let us do parse it. Saptak and Kundan, could you parse it using the LL1 parser? So could you guys parse it using the LL1 parser? Okay, good, good. So let us just do it once for clarification and then we will go ahead. So for example, we want ID plus ID. Using the LL1 parser, we have to do it. What do? We'll place ID plus ID on the stack, on the what do I say? It should be input buffer, and place dollar at the bottom, at the end, and this is our stack content. So initially we have dollar in the stack, right? Now, and we will place S at the start symbol. So over here we have the start symbol as E. So then I'm just telling you how the parsing is done using LL1 parser. That is what I'm trying to do. And what are the steps basically? If the start symbol, so what are the steps basically? If the start symbol, so what are the steps basically? So for example, what do? If a non-terminal is there, you match that non-terminal. And so for example, on the stack there can be a non-terminal or can be a terminal. If it is a non-terminal, then corresponding to the input pointer, you will see that entry. If that entry is an error, then it is an error. If that entry is some production, you are going to push that production onto the stack. Good, good, Anand. Very good. So let us do that. No issues. So by actions you mean pushing also and popping also, Anand, right? Pushings only can be not more than 8. There will be 8 pushings. We counted it, right? 9 pushings. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, yes. Okay, no issues. There cannot be more than 9 pushings, right? Okay. So, so if this symbol is, so in that case, if it is a non-terminal and a terminal, so on the input buffer you will always find a terminal. Then in that case you are going to push that production, the right hand side of that production on the stack. That is one thing. If it is an error, then you will report a syntax error, right? Now what happens if it is a terminal? If it is terminal on the input stack also, then if that terminal matches with the terminal on the input buffer, then you are going to pop that and move ahead. If it is dollar on both the places, then you are going to accept. And if the terminals don't match on the stack as well as the input buffer, then you are going to report an error. So that's what the entire algorithm is, right? So if the non-terminal is there on the stack, then you are going to see the cell corresponding to that non-terminal and the column corresponding to the terminal on the input stack, input buffer. If that is an error, then you are going to repeat an error. If that is not an error, then you are going to push that production from the right hand side of that production on the stack. If it is a terminal, in that case, if the terminal matches, you are going to pop and move ahead. And if it is dollar on both the places, then you are going to accept. And if it is not matching, then you are again going to report an error. That's what we are going to do. Let's do it. Now E on ID. What is E on ID? E on ID is use the production number 1. So E on ID says use the production number 1. What are we going to do? Dollar What is production number 1? TE dash. E goes to TE dash. So I will write in the reverse order. E dash and then T. E dash and then T. Right? This is first step. So E on ID is basically production 1. Production 1 is E dash T. I have put on the column. Put over here. Right? Now T on ID. So ID will remain over here only, because when the symbol matches only, then only I am going to do. So now you can see that the first step is almost done. This expansion is done. E goes to TE dash. This expansion is done. I'll keep on marking over here also. Right? Now over here, if you see, T on ID. T on ID should be again expanded to FT dash. Let us see whether it does or not. T on ID is production number 4. Production number 4 is FT dash. So T on ID will become $E dash. Okay, the space is less. So what should we do? Okay, well, I'll manage in this space. I'll keep on rubbing. Right? So what I will have is $E and T will be replaced with FT dash. So T dash will come here and F will come at the top. So even this expansion is done. So we need to do 9 expansions, right? Now F on ID. F on ID, if you see, it is basically production 7 which is being used, and if I replace F with ID, what I will get is, where is eraser? F on ID will give me, ID here. So my pointer is here only and my stack looks like this. So I'm done with this expansion also, and now my ID will match with ID. I'll pop ID and then I'll move over here. Then I'll move over here from here, right? And now this ID is also gone. So what I will have in the stack is, what I'm doing erasing business over here only, because so as to save space, you may write down in other steps also, right? Now you tell me what is T dash on plus. So this all business is done now. So what I need to do, 1, 2, 3, 4, 5, 6, 3 plus 3, 6 more expansions needs to be done, right? So now T dash on ID. So how the question can come in GATE exam? They can ask you the configuration at any point of time. They can ask you whether the grammar is LL1 or not. Then they can ask you fill the contents of the parsing table. They can ask you the cells of the parsing table. That's all. Nothing else can come outside this. Or the theoretical question, conceptual question, what happens in LL1 parser, why it is called LL1, and so on and so forth. That's it, right? So $E T dash is done. Now T dash on plus, tell me, T dash on plus. T dash on plus goes to what? T dash on plus gives me expansion number 6. T dash on plus gives me expansion number 6. Expansion number 6 is basically epsilon. It will replace this T dash with epsilon. So what I will have is this T dash will also be chucked out. T dash will also be chucked out. So I am left with this stack, and my pointer is still here only, right? Till this everything fine. Now E on plus. What is E on plus? E on plus. So even if you check, this is also done now. 4 things are done, 5 are left. Now E on plus. Again I am E and plus. E on plus is again, sorry, I have TE dash now, sorry. So E dash on plus I have to check. E dash on plus is basically production number 2. What I will do is I will write E dash T plus. So I will write it as $E dash will be chucked out, and I will have again E dash T plus. Okay, so it will come as, I'll write it over here only, T and plus. This is what I'm going to get. This is what I'm going to get. This I'm not needing, right? So till this everything is done. Now we have plus on a plus. Now where plus on a plus is basically you will pop it out. Now your stack pointer will move over here. This is your stack pointer now, and plus is popped out. So if plus is popped out, it will look like this. So this is your stack now. So you have T dash E dollar and ID over there. So now plus is also mapped, that is fine, and even this expansion is also done now. So 1, 2, 3, 4, 5 expansions are done, these are left. Now T on ID, tell me, T on ID is going to give me 4. T on ID is going to give me expansion 4, which is FT dash. This one, this expansion is being done now. Okay? So T will give you FT dash. I will place T dash over here and F over here. Right? So this is also done now. Now F on ID, tell me, what is F on ID? F on ID is basically an expansion of F on ID. Let me check from here. F on ID is expansion of 7. So if I expand 7, I will get an ID over here instead of F. I will get an ID over here instead of F. I will get an ID over here instead of F. Now ID on ID. So even this one is done now. ID on ID. ID on ID is going to give me acceptance. Popping up. So ID with ID is mapped. So therefore I'll move over here. My input pointer will move over here and this ID needs to be checked out. This is the current situation. Right? Now, now T dash on dollar. T dash on dollar is 6 number. Number 6 is epsilon. So this T dash will also be checked out. Check. So now we have E dash and dollar with us and this is also done now. Just this expansion is left and then we are done. Now E dash on dollar. E dash on dollar, if I see, it is number 3. Number 3 is basically epsilon. So this will also be checked out and this is also done and this will also be checked out. Then it is dollar on dollar and you accept. So if you see, whatever was simulated by us in the example has also been done by the LL1 parser also. And I hope if you do this one complete example, the entire concept of LL1 parser has been revised. Right? Is everyone fine till this point or not? Is it okay, everyone? Please tell me, guys, is everyone okay or lost? Fine, sir. Okay. Good, Anand. Very good. Avilash is also okay. What about Sovik? So, and what, who else was there? Saptak, Sovik, and there was one more guy. Who was that? Saptak, Sovik, and Kundan. Yes. Some of the guys skipped, you know. In the break, they slipped out from the session. Anyways, no issues. So, guys, okay till this point. Let's move to the next parser, which is operator precedence parser, which is a bottom-up parser, right? And this is the only parser which can handle ambiguous grammars also. But so again, in operator precedence parsers, the questions can be of operator precedence parsers. So operator precedence parsers, the questions can be of again 3 types, whether the grammar is operator precedence grammar or not, whether the, okay, Kundan is back, good. So whether the grammar, whether the given grammar is an operator precedence grammar or not, first question. Second question, construct the parsing table. Third question, check the configuration. We'll repeat all these steps on this given grammar, right? That will make this concept very clear about operator precedence parsers, right? So once we do this, then we are left with 4 parsers. All those 4 parsers will have the same parsing algorithm. Nothing needs to be done on that front. We'll just do one and all 4 will be done. But we have to construct the parsing table of each of them, that we will do. So that much work is left. I hope it is fine. So Abhilash, Anand, Kundan, is it okay? Can we continue? We might go till 9:15, 9:20. Would it be okay? A bit delayed lunch, a bit delayed dinner. Would that be okay? Right? Abhilash is fine. Anand and Kundan, is it okay? Can we extend it to 9:15, 9:20? Is it okay, right? Yeah. So Abhilash is okay with this. Anand is also okay. And I hope Kundan is also okay. Okay. So operator precedence, when we say what is the condition, when do we call a grammar is operator precedence grammar? When the productions are of the form, so A goes to epsilon is not allowed and A goes to BC is also not allowed. That is, no two non-terminals should be together. Two terminals can be together, but no two non-terminals should be together. So is this grammar operator precedence grammar? No epsilon is there and then it says A goes to BC. No. So there is always a terminal. There is always a terminal. So this grammar is an operator precedence grammar. This is done. So that's the condition. Now when I say this condition, then we need to make the operator precedence table. In what is the operator precedence table? What is there in the rows and what is there in the columns, guys? What is there in the rows and what is there in the columns? 1, 2, 3. So plus multiply ID and dollar. So plus multiply ID and dollar. So all the non-terminals, all the terminals both on the rows and columns, right? And we are going to write the associativity and precedence, the precedence of each of them, right? So we always know that ID has the highest. So what is this side? This is left, this is right. This is stack and this is left, right, and this is stack and this is input buffer. Now let us do. Okay, so dollar has the least precedence, we already know, and dollar on dollar is acceptance. ID has the highest precedence, we already know. Oh, it looks bad. Let me take a different color. Undo. Right? Now ID has the highest precedence. ID on ID is error. ID has the highest precedence. This much table is filled. Right, very good, Abhilash. So Kundan, I think you are confused with LR0 parsers. This is not LR0. Very good, very good. Now plus on plus. Now by seeing this grammar, we see this is left recursive. So therefore, left side plus is more having higher precedence. It is left associative. Similarly, with multiply also we see left recursive. Therefore, multiply has higher precedence, left wala. Among multiply and plus, multiply is farther. So therefore, multiply has higher precedence. This multiply has higher precedence. Right? This is how you construct the operator precedence table. Right? Correct, Abhilash. Very good. Now this is done. Now what is the next step? This is first step. This is second step. Now then let us take a string. Let us try to find out ID plus ID cross ID using this grammar. So let us generate the parse tree first and then we will see whether that is being done or not. So let us generate the parse tree first. So ID plus ID cross ID. Generate the parse tree, guys. Tell me how it looks. This is how it looks, I hope. So again, this is a bottom-up parsers. You need to do reductions. How many reductions are required? If you see 1, you require 1, 2, 3, 4, 5, 6, 7, 8, again 9 reductions. No, 8 only, not this. 8 reductions, right? So 1, 2, 3, 4, 5, 6, 7, 8. 8 reductions, right? Guys, please cross check and tell me. 8 reductions we need. So how is the parsing table? How is the parsing algorithm in operator precedence parser? We place $, in the beginning. And then we try to parse the string. Right? Is it? Yes, so you are getting 8 or not? Tell me. Right? Okay, good. So now how the parsing algorithm works? We have $, at the bottom of the stack, and then we are going to compare the input with the stack top. Right? We are going to compare the input with the stack top. Right? And there will always be. So again, what are we going to do? We are going to start with ID plus ID cross ID. Right? And then what we are going to do is, if the stack top is heavier, so that what does it mean is, if the precedence of the stack top is greater than the input buffer, then we are going to pop. If it is less than or equal to the input, then we are going to push. Right? That's it. And whenever we are popping, we are going to do the corresponding reductions. That's how it is. Okay? So okay. So what I'll do is, I'll take this over there so that we can do it faster. Let me select it. Okay, let me take this. This is not needed. Undo. So I need this table and this on the next page. Let me take them one by one. It's not coming up. So let me just take the table, we'll reconstruct it over there. Where is select? Let me just take the table, then we'll reconstruct it. Copy, next slide, paste. Table is okay. Okay. Okay, anyways, let it be like that. Somehow this feature is not working properly. I'll do it on the previous slide itself. I'll remove something from there which is unimportant and I'll do it over here itself. Let me remove this part. This you already know, I hope. I can remove this. Right? Let us do it here. This part can be a bit smaller. But it is undo. Yes, now it's okay. This much space will be okay. Okay. So we require 8 of them. That's correct. So we'll require some 8 of them. Let us do it on run the algorithm that we have. So we'll have the stack with us. The stack will have initially. So this is my input buffer. It is ID plus ID cross ID. And in the stack top, I'll have dollar. So dollar when compared with ID, we know that dollar with ID, ID has higher precedence. We already know. So when higher precedence operator comes, we push ID over here. Now ID with plus. So when ID is being compared with plus, ID has higher precedence. Right? So in this case, what you are going to do is pop. So when lower priority thing comes up, you are going to pop. When higher priority things comes up, you are going to push. Okay? So ID on plus, you are going to pop. So when you pop ID, you are going to do the corresponding reduction. What is that reduction? F goes to ID. So this reduction is done. I will show you that this reduction will be completely done in the same way, the way we constructed it. Right? F goes to ID is done. Now, this ID is already gone from here. What do we have? Dollar and plus over here. So when compared with dollar and plus, when I compare dollar and plus, tell me what is the order? Dollar and plus. Plus has higher operator. Plus is a higher precedence. So plus will come. Then plus and ID. ID has higher precedence. ID has higher precedence. So ID will come inside. So now my pointer is, so ID has also come inside, plus has also come inside, my pointer is over here. Now ID with dollar, ID has higher precedence, ID will be popped out. So this reduction will be done. So what I will have is, this ID goes away. I will have this situation. Now plus with multiply. Multiply has higher precedence, we know. This is the current situation. And ID will go to ID. Now ID with multiply. Who has higher precedence? ID always has higher precedence, so ID will come over here and sit down over here. Then we have a dollar. So now the pointer is at dollar. Now ID with dollar. ID has higher precedence, we know. ID will be popped out. And the corresponding reduction for ID, whichever is the reduction possible, will be done. This is also done. So out of 8 reductions, we have already done 3. And then we will see all of them will be done. Right? So then what we have to do is, ID plus ID cross ID is fine. And then we have a dollar. Okay? So multiply with dollar. Who has higher precedence? Multiply has higher precedence. Multiply needs to be popped and the corresponding reduction needs to be done. But for doing this reduction, T multiplied by T cross F, we require one more reduction. So therefore 2 reductions will be done. F goes to T as well as T goes to T cross F. So all this is done after removing multiplication. Now plus is compared with dollar. Again plus has lower precedence. Plus has higher precedence. So therefore plus will be popped out and all the corresponding reductions needs to be done. That will be done for plus. For plus requires E equals to E plus T. So this F will be reduced to T, T will be reduced to E, and then E plus T is obtained, and this entire thing will be obtained. And then dollar will be mapped with dollar. That will give you acceptance. That will give you acceptance. Is it okay? Yes, Anant, Abhilash and Kundan. Tell me, is it fine? So the idea is very simple. If the higher precedence operator is coming, push it. If lower precedence operator is coming, pop it and do the corresponding reduction. Right? So this completes operator precedence parser. What is the next parser? LR0 parser. Operator precedence is done. Next is LR0 parser. So LR0 parser is another bottom up parser. What do we need to do? LR0, SLR1, LLR1, CLR1, all of them are there. But let us discuss LR0 first. What do we have to do? We have to form the canonical collection of LR0 items. For that, then only we can construct the parsing table. And once we have the parsing table, then we'll do the. Then what we will do? Once we have the parsing table, what is it that needs to be done? Apply the parsing algorithm. Right? This is how it is done. Right? So first of all, let us draw the canonical, make the grammar augmented. Yes, very good. That has to be done. For the first thing that we need to do is make the grammar augmented. So first of all, we'll have s dash goes to dot hash. And then we are going to find out canonical closure, and we'll make a canonical collection of the closure canonical LR0 items. So we'll make a canonical collection of the LR0 items. Right? And that looks like a deterministic automata. So s dash goes to dot s, and then we are going to expand every symbol. S goes to dot a and a goes to dot aa. So yeah, because of this a, we are going to expand this, and a goes to dot b. So this will be your first state, I0. This will be your first state, I0. S dash goes to dot s goes to dot a goes to dot aa, and a goes to dot b. So you can parallelly construct it, right? Okay. Right? Now what happens if an s comes? You are going to get s dash goes to s dot. If an a comes, you are going to s goes to a dot a. S goes to a dot a. And then we have, because of this a, I will expand further. Just a second, guys. So s goes to a dot a, then we have a goes to dot a and a goes to dot b. How? When do we expand? When we have a non-terminal. After the dot, we expand that non-terminal, right? So this is done. Then we have small a. Small a will give us a goes to a dot a, and this a will again expanded. A goes to dot a goes to dot b. And the last thing is when we get a b, we'll get a goes to b dot. Right? So these are the states that you are going to get. So these are the states that you are going to get. Right? Is it okay till this point? Everything matching or not? Tell me, guys. Abhilash, Anant, Kundan, everything fine? Now, what else we need to do? Yes, good, good. Now, this cannot be further expanded. Let us expand this. We'll get S goes to AA dot. Done. What else? What if a small a comes? It will be this kind of behavior. I will go to this A. If a small a comes, I will get A goes to A dot A. This is the one. If a small b comes, I will come back over here. If a small b comes, I will come back over here. Now what happens? What happens on this state? If I get a capital A, in this case, I will get a new production, which is A goes to a new state, basically A goes to AA dot. So all the productions are reduced now. Now what happens if an A comes, small a comes, you remain over here. And what happens if a small b comes, you will come back over here. Right? This is the canonical closure of the LR0 items. Right? Everyone fine till this point? Now we will construct the parsing table. So how do we do that? We just make the grammar augmented. Once the grammar is made augmented, we are going to write the canonical closure. So how do we do the canonical closure? Whatever is that non-terminal after on the right hand side, you are going to expand that non-terminal. You are going to expand that non-terminal, whatever non-terminal you see. Right? And you are going to take corresponding transitions to move the dot further. What does dot represents? Symbols on the left hand side of the dot have been seen, and the symbols on the right hand side of the dot are yet to be seen. Right? So let me make the parsing table now. So what are the contents of the parsing table? What is the size of the parsing table? What is the size of the parsing table? What is the size of the parsing table? Tell me. How do we make the parsing table in this case? So we'll have the states. So what are the state numbers? Let me give the numbers to the states. I0. Let me use a different color, otherwise it will be confused. Okay, which color I have not used this one? This is I0, this is I1, this is I2. This is I0, this is I1. This is I2, this is I3, this is I4, this is I5, and this is I6. Right? 7 states are obtained. Right. Number of states will be 7. Number of states are 7. Right? Everybody is getting the same. Now you are going to construct the parsing table where you will have I0, I1, I2. I will require 7 rows. Require more space. Let me write it like this. I0, I1, I2, I3, I4, I5 and I6. What will come in the columns? All the terminals as well as non-terminals. So what does the non-terminals contains? The go-to actions. And the terminals will contain the shift and reduce actions, right? So what is I0? Just tell me what will come in I0. So what will happen in I0? On S and A, you are going to I1 and I2. So you will go to state number 1 and state number 2. This is go to action. And this is shift and reduce action. Right? So this is not called action, this is just go to, and the actions are shift and reduce. So now what is I naught comma A? I naught and A is shifting to first state. I naught and A is shifting to third state, S3. I naught and B is shifting to fourth state, S4. Right? Is it okay? Now, I1 on A. I1 on A. I1 is not doing anything. I1 comma dollar is accept because the augmented production has been reduced over there. So this is accept. If you get this configuration at the end of your parsing, then the string is accepted. That's it. Now I2 on A. I2 on capital A goes to I5. I2 on small a goes to I3. And on small b goes to I4. That's it. Yes, 4 and 3 and 4. Now I3 on small a goes to I3 itself. Small b goes to S4. And on capital A goes to 6. Capital A goes to 6. Now I4 is just a reduction state. This is the first reduction. Now when do we reduce in LR0 parser? Where are we going to place this? So we will name the productions. The productions will be named R0. This is the first production, this is second production, this is the third production. And to tell that the third production has been reduced, I will write R3 under all the terminals. R3, R3, R3. R3, R3, R3. I4 on B is reducing. Yes, it is reducing on everything. Since it is LR0, it will be reducing on everything. Right, Kundan? Now, I5 is also a reduction of the second production, that is the first production. So I5 will be R1, R1, R1. And I6 will be R2, R2, R2. Is this table clear to everyone or not? Or is there some mistake? Just let me know. I hope it is correct. So Anant, Kundan and Abhilash, are you getting the same table or not? Good, good, Kundan. Right, this is the table that you are going to get. Now once we have the table, what is the next step? What is the other thing that can be asked? Yeah, tell me, what is the next thing that can be asked? Is everyone getting the same table? right? Yes, the grammar is LR0 or not, that can be asked. For that you will have to check the parsing table, and in this parsing table, since there is no conflict, there it is an LR0 grammar, right? Anand, very good. And you can also be, what can be asked is to, it's the contents of this table. That is also the second thing. And the last thing is, given a string, you can be asked about the configuration of the input buffer as well as the stack, right? As well as the stack, whatever is that can also be asked, right? So let us see. Try to apply this reduction. Try to apply this parser on one of the strings, and then we will be able to complete this parser also. And this algorithm needs to be discussed only once, because LR0, SLR1, LLR1, CLR1, all of them are going to use the same algorithm. But before we do that, tell me, what if I have an SLR1 parser? What will be the change in the table? If I have LR1 instead of LR0, I am having SLR1. What will be the change in this table? Right, very good. So let me take a copy of this and take it to the next slide. I hope the copy works well. Copy. Next. Paste. अरे यार ये नीचे आ जाता है. So yes, so this is the table that you are getting, and what will be the change if I try to make SLR1 table of this? So the only change will be there will be a slight change in the table. So what is the change? The LRs, the reductions will only be placed in the follow of the left hand side. So there are I4, I5 and I6 have reduction steps, right? Only I4, I5 and I6 have reduction steps. I4, I5 and I6 has reduction steps. So what is the change? So first of all, we need to check the follow of R3. For R3, we need to get the follow of A. Follow of A is nothing but A, B and dollar all. Why? Follow of S is A. Follow of S, if I calculate, follow of S will be dollar only. Now follow of A will be first of A. First of A is A, B both. And follow of A is also equals to follow of S. Therefore, A, B and dollar all will come. So follow of A is this. Now since this is known to us, what will only happen is this reduction will only be placed under dollar, else all the reductions of A will be placed under all the rows. So therefore, R1 will only be placed under dollar, else everything remains the same. So what will happen is we will remove this, and that's it. Else everything remains the same. Right? There is no other change. So this completes your SLR1 parsing table, and this is your LR0 parsing table. Right? And let us parse a string now, and that will complete both the parses together. Right? Right. So now let us take a string. That string is AABB. Can you guys generate that string using the given grammar? The grammar is with you. This is S goes to A and A goes to A and slash B. Let me write it over here also. S goes to A goes to small a comma B. I want to create AABB using this. So how would we create? S goes to AA. Now, I want more A's. So from this A, I will produce more A's. Right? Now I can produce a B from this A and I can produce one B from this A. Did everybody got the same parse tree or not? Tell me. Is the parse tree same or not? Right? So this will be the parse tree. Now how many reductions are needed? 1. How many reductions are needed? 1. All the known leaf nodes. 2, 3, 4, 5, 6, 7, 8. 8 reductions are needed. If I count the known leaf nodes, 1, 2, 3, 4, 5, 6, 8 कैसे आया? Just let me check, guys. 1, 2, no, this is also not counted. 1, 2, 3, 4, 5, 5. Let me undo it. I counted it wrongly. Sorry for the typo. I have to count the lone leaf nodes. 1, 2, 3, 4 and 5. 5 reductions, right? Sorry. I have to count the known leaf nodes, right? So let us see whether the parser also does the same or not. How does this parser works? We are going to place I0 at the bottom of the stack and then we are going to read the input buffer with the first state and with the, so corresponding to the state and corresponding to the input buffer, corresponding to the state on the stack and corresponding to the terminal on the input buffer, we are going to check what? The action. If the action is shift action, you are going to push. If the action is reduce action, you are going to pop. While popping, you have to pop twice the number of symbols on the right hand side of the production. Twice the symbols you have to pop. And then after popping, you are going to push back what? The left hand side. And whatever is there on the bottom, so, and there will be some state at the beneath it. So that state and that non-terminal that you are pushing, that will also have a go to action and that go to action will also place another state which is in the go to. So let us see this step by step. I am not writing the detailed algorithm because of the scarcity of the time, but what I will do is I will just apply the algorithm over here and then see whether we are able to generate it or not. That is what I am trying to do, right? Now, and the input pointer will only move when we are pushing. During the pushing, the input pointer will move, right? So, and okay, so let us take this on this example and let's say our input pointer is right now at A and let us write down the contents. So initially you have I0 on the top of the stack. Tell me what happens on I0 on A. Tell me, guys. Keep on replying. I0 on A, what does it give? I0 on A goes to shift 3. Shift to 3. That means shift to 3. That means we are going to state number 3 and push I0 on A gives shift 3. You will have I3 over here. This is done. Very good. Now I3. So since we have shifted, we are going to move ahead. Pushing will move you ahead. I3 on A, tell me. I3 on A is again S3. So again you are going to push. You are again going to push S3. Now your pointer will move over here. Now tell me, I3 on B. I3 on B says, I3 on B give me S4. So the content will look like So the contents will look like, I'll go to I4. I'll go to I4. Right? Is it okay till this point? Very good. So then we have I4 on B. Now the first reduction will be done. I4 on B reduces the production number 3. What is my production number 3? This is A goes to B. So when I reduce it, I will pop out twice the number of symbols that I have. I have one symbol over there on the right hand side. I'll pop 2 symbols and then I'll get, what I'll get? I will get I0, A, I3, A, and then I have I3. What will come on the top? The left hand side. What is A? What is I3 on A, guys? I3 on A gives me 6. So I will go to state number 6. This is my current state, and I have done one reduction, which is B goes to A. So this part of the tree is done. This part of the tree is done. Everyone fine till this point? This part of the tree is done. Very good. So I6 on B. Now tell me I6 on B. I6 on B is giving me reduction. Second reduction needs to be done now. I6 on B gives me R2. So second reduction will be done. 2 symbols are there. We are going to pop 4 symbols now. 4 symbols. This will be gone. This will be gone. This undo. This will be gone. This will be gone. This will be gone. This will be gone. What I'll push? A. I3 on A. I3 on A gives me 6. So I will have I0, A, I3, and then we'll have I3, yeah, so currently the pointer is here, right? We have already pushed one B and we are on the last B. So I3 on what? Capital A. So what has to be pushed? I3 was there. We have to push capital A and I6 will come over here. This is the current configuration. Now you have to tell me what is I6 on B. So even this reduction is done now. This much part of the tree is completed. This much part of the tree is completed. Now I6 on B. Tell me what is I6 on B? I6 on B is R2. Again I have to reduce. This reduction will be done. So I6 on B will be R2. R2 if I do, I have to pop out 4 symbols. What are the 4 symbols? 1, 2, 3, 4. Double of that. And I will push A, and I0 on A goes to nothing but 2. I0 and A goes to nothing but 2. So once I did this, this much tree is done. This part is left only. This part is only left. Now tell me, I2 on B. I2 on B is shifting to 4. Now this B is also pushed, and after that we have a $. Now B is already pushed, and now I2 on B is shifting to 4. I'll go to S4. I4. So now I4 on $. Now the pointer has moved since we have pushed. Now I4 on $, tell me how I4 on $, will reduce 3. Third production, that is this one. So therefore this reduction is also done now. So I4 on B will pop 2 symbols, and once we pop 2 symbols, we are going to write capital A and I2 on A. I2 on A takes me to I2 on A takes me to I5. Now tell me I5 on $. I5 on $. Will take me to the reduction number 1, that is what I am waiting for. That is S goes to A will be reduced. Now how many symbols will be popped out? 1, 2, 3, 4. And this completes this wala reduction also. Now after popping this I naught, what I will have? I naught on what? I naught will come and what will come on the stack? Capital S. I naught, capital S, and which state I will go? I naught and S goes to nothing but I1. Now I1 is there and dollar is there, we accept. Right? I hope you could quickly refresh. I quickly, refreshed LR0 and SLR1 together. And when we talk about LALR1 and CLR1, everything remains same, nothing changes. At least the algorithm remains the same. The only change is we are going to take the canonical closure of LR1 items instead of LR0 items. Is this fine till this point or not? Tell me, guys. Is it okay or not? Right? Yes? So what you have to do while doing this, so this is LR0, SLR1 is same. In CLR1 what you have to do, you have to take the canonical closure of the LR1 items, rest everything remains the same. Right, rest everything remains the same. And in LALR1 what you have to do is, this is CLR1. In LALR1 you are going to merge the states which have similar LR0 items but different LR1 items. That's it. Right? So else everything remains the same. This is the only change, that we are going to use LR1 items, and everything else, that is the algorithm, remains the same. There is no change in the algorithm. So let us quickly calculate. The canonical closure of LR1 items for this grammar. S dash goes to dot S. Now what is LR1 item? We are going to write the follow along with the production. So S dash goes to dot S comma dollar. What will come next? S goes to, what was the grammar? S goes to dot A. And what is the follow of this? This is dollar. Now what comes after that? A goes to dot AA, and A also goes to dot B. But what will be the follow now? Follow will be first of this part, whatever is following this A. Now first of A, do we know what is first of A? First of A is nothing but A and B both. First of A is nothing but A and B both. So we are going to write A slash B and A slash B over here. So this is your first state I naught. Okay, is it okay? Right? Is everybody clear till this point or not? Tell me. Anant, Kundan, Abhilash, is everything fine? Okay, good, good. So now you tell me, I have to write a bit smaller now because this has more states and the number of states I might exceed the space. So now S. Now what happens on an S? S goes to S dot. So on the transitions nothing changes. The only change is with when we are going to expand. While expanding, you have to take the first of the part which is following that variable, right? Whichever variable you are expanding, right? So over here, now what happens if an A comes over here? You will have S goes to A dot A, comma dollar. Now A needs to be expanded. Now let me expand A. A goes to dot A goes to dot B. That's it. Now this A is expanded, and now what is the follow of this A? This A is follow is dollar. This is the next state that you are going to get. Okay, till this point. Now small a. Small a will take you A goes to A dot A, comma A comma B. Now this needs to be expanded. Now this A needs to be expanded. What are you going to get? A goes to dot A comma A. What is the follow? What is the follow now? AB. Follow of this A. Now A goes to dot B. Follow will be AB. So this is the next state that you are going to get. Now what happens on a B? You are going to get A goes to B dot, comma A comma B, A slash B. This is going to be your next state. Till now how many states you get? 1, 2, 3, 4, 5. Right? Is it okay? Is everyone fine till this point? Tell me guys. Right, good. So I need some space. Let me just minimize it a bit. Okay. Now, this cannot be expanded further. Let us expand this. We'll get undo. Okay. So this needs to be expanded further. This cannot be expanded, but this can be expanded further. If I get an A, I'll get S goes to AA dot, comma dollar. The first reduction is done. Now after that we have small a. So if I have small a goes to A dot A and A goes to, that's it. Now this A has to be expanded. A goes to A dot A, but this is different from this one. How? Because we have dollar at the follow. Now this A will be giving you A dot A comma dollar, and this A will also give you A goes to dot B comma dollar. Sorry, yes. Yes guys, tell me now, is it audible? Kundan, Amrita, Anant, is it audible now? Yes, good, good. Anyways, so okay, so just let me finish it till this point. Everybody is getting the same canonical closure or not? Tell me guys. This is A, this is B, this is fine. Now this state is left. Now what happens if an A comes? This is A will go to AA dot comma dollar. A will go to AA dot comma dollar. And then done. This state is also done. Now what happens if an A comes, small a comes? There will be a self loop again. And if a B comes, there it will go to this state. So this is how we will make the canonical closure, and we'll make the table in the same way, the way we made earlier. Right? So the shift actions will be placed under the shift and reduce actions will come under the terminals, and the go to actions will come under non terminals. Right? What will be the change in the LALR1 parser? The terms which are having the similar LR0 items will be merged, but different LR1 items, they will be merged. How? So let me just take this example and tell you which states will be merged. Tell me guys, which states will be merged? Let me number the states. Tell me which are the states that are going to be merged. Which are the states that are going to be merged? I3 and I6. Okay. Yes, we can merge I3 and I6. We can also merge I4 and I7. And I can also merge I8 and I9. So first you have to make CLR1. First you have to make this, and then you are going to see where you can merge. Right. I3 and I6. Let me check. I3 and I6. I6 I should have written. Okay. Sorry. It should be I3 and I6. Right? Good, good. So this is basically I3, I6, I4, I7 and I8 and I9. We are merging all these states. And then we'll get a merged parsing table, and everything else remains the same. Okay? So one last point. If the question demands for checking whether the grammar is LR0, LALR1 or not, CLR1 or not, how you are going to check? Just check if it is LL1 or not. If it is LL1, then you can simply say it is CLR1 also as well as LALR1 also. Why I am saying this? Because LL1 is a subset of LALR1. That is why I can say this. If the grammar is not LL1 and it is also not CLR1, do not check for LALR1. It will also not be LLR1. And if the grammar is LL1, it is not LL1 but it is CLR1, then you have to check for LALR1. How would you check? You will see if the states that are being merged are having two reductions, and if that reductions are going to produce similar follow items. So only check the states which are having, only check the merger of states having two reduce moves, two reduce actions. And if the follow of those reduce actions, match at any of the terminals, then we will say that it is not LALR1. Yes, the look ahead symbols match. So whatever we are writing in the look ahead, that is basically the follow, right, of that production. Right, Kundan, you are correct. Right. So this completes the full revision of the course of compiler design. Right. So that's all about today's session. I hope I could simply take you through all the entire content, right? I think yes. Right. Okay. So that's all about the parsers and the compiler design. Okay. So I hope you understood everything, and I could not cover the things in detail because again, as I said, this is a revision session. I cannot cover the 40 hours content in the same way which I cover in 5 hours. What I did is I quickly took you through all the concepts so that those who have already done it, it gets refreshed in their mind within 4 to 5 hours, right? So I hope all of you understood properly, and if there are any doubts, I am there on the doubt portal also. So you can post your doubts on the doubt portal, right? And just remain focused for the remaining days. You are definitely going to make it big, right? So wishing you all the best for the coming GATE exam. See you all. See you all again once you get the good GATE ranks, right? So yeah, so I'll share the PDF, Kundar, not an issue, right? Okay. So all the best people for your exams, and see you again. Okay. Good night, everyone. Good night.